Welcome back to my today's session, Application of Time Varying Field. As we discussed in the last class about the different type of fields, and there we discussed about there are three types of field. Namely, first one is the electric field, magnetic field, and the electromagnetic field. Again, electromagnetic field is two types, static field and time varying field. Today our discussion is purely based on the time varying field and its application. So before starting, we will start what is the electromagnetic field, or what is a field? A field is a function of specific quantity in the region. We can tell a function that specifies the quantity in a region or a space. So say I am telling there is a field where you go daily and play your matches. So this is you are playing cricket. So we can tell this is a cricket field. Same like this, in an area, if we keep some things and it will feel some electrical force, we will call it electrical field. A field is nothing but a spatial distribution, like a space. So all the points are some distribution, so spatial distribution of a quantity. In general, it can be scalar or vector in nature. You can see this is a transmitter and this is a receiver. Whatever you are telling from here, this is in the electromagnetic waves. It is going from transmitter to your mobile or to your landline. So this is a field. This is a field from this area. We can tell this is a field, and this is an example of electromagnetic field. So what are the electromagnetic field? Already I discussed in the last class. Just a quick recap: electric field, magnetic field, and electromagnetic field. Electromagnetic field is again two types: time independent, and this is due to the AC current, and this is due to the direct current, and or otherwise a constant electromagnets, and the time varying field is due to AC, or we can tell the magnet is varying. So you, as the name tells it, this field is due to the electricity and due to the magnet. So it is two types. One is the DC field, it is due to the DC, and the magnet is fixed. And for the AC, the magnet is also varying, the current is also varying. So now we will discuss about the how time varying fields are developed. You can see from the equation we can tell time varying fields are produced due to the accelerated charges or time varying currents. What is the meaning of the time varying current? Current which is changing with time, and we can tell as the AC. And we can also call this as the accelerated charges. Charges are moving with the speed, with a velocity. Now, a time varying field is produced by a time varying magnetic field. If we rotate the magnets, there is a magnetic field, or if we are moving the magnet, there is a time varying magnetic field and the time varying electric field. So, time varying magnetic field and time varying electric field, if both are reacted together, if both are coupled together, we can get a electromagnetic field. You can see the green one is this green one is the electric field, and the blue one is a time varying magnetic field. If I show the video, you can see that both are changing continuously. So what does it mean? As a result, in this area we get a electromagnetic field. And this first concept was experimentally introduced by the Michael Faraday, but Michael Faraday doesn't know the mathematics or the physics behind it. What he did, he took one coil, he gave some AC current, normal current, and he moved one magnet inside, and he got a time varying field. But later, after 50 years later, the James Clerk Maxwell, this is the Maxwell first mathematically proved how the electromagnetic field is established in the in an area. So that's why Michael Faraday and Maxwell's are known as the fathers of the electrical engineering or electricity. So, what is the electromagnetic induction? So, electromagnetic induction, while there is a change in magnetic field, it is maybe the changing intensity. It is the movement of the magnets, as I told earlier. There is an induced field in it. There is an induced field in it, and as if the circuit is closed, then it will give some current to flow. So a changing magnetic field will induce an electromotive force. This is called the electromotive force. We write by generally E, and it is similar to the velocity V. So mathematically it is similar to the velocity V. So if the circuit is closed due to the electromotive force, the electrons will start to move in the closed path, and as a result the current will start in the path. So based on this, Faraday has given the three laws. Faraday's first law. What is Faraday's first law? Any change in magnetic field of a coil or wire will cause an induced an EMF, and this EMF is known as the induced EMF. And how we can change the magnetic field? The magnetic field can be changed by moving the magnet to and fro towards the coil or taking away from the coil. Next, by moving the coil into the magnetic field. This is we can used in the any motor or any generator. There is some magnetic field, north pole and south pole, and there is a coil. What we do using the prime mover, we rotate this coil, and as a result EMF is induced. This is the main working principle of any generator. This is the main working principle in a generator. In a fixed magnetic field, if we move the north pole and if we move the coil, if we rotate the coil using the prime mover, then what will happen? Or using the shaft, it will induce some current and EMF in it, and this is the main working principle. Then by changing the area of the coil placed in the magnetic field, if we change the number of turns or number of the area, then also it will that magnetic field density will change, and as a result the EMF will induced. And by rotating the coil relative to magnet. One is the movement, another one is the by rotating the coil. This is also the generator thing. So this is the Faraday's first law. What is the Faraday's second law? Now we will go to the Faraday's second law. So Faraday's second law states that the magnitude of an EMF in the coil is equal to the rate of change of flux that's linkage with the coil. The flux linkage of the coil is the product of number of turns and the flux associated with it. So what does it mean? If there is, and as we discussed that the flux is a time varying flux, so if there is a rate of change of flux, then only EMF will induce. We can write in EMF E is directly proportional to the d phi dt. So if there is a rate of change of flux, there will be an EMF will be induced. And we can write E is directly proportional to N d phi by dt. N d phi by dt, and E equals to minus N d phi by dt. E equals to minus n d phi by dt. So this is the Faraday's law. So from where this minus came? So minus came from the third law of the Faraday's, which is again known as the Lenz law. We can discuss. So what is Lenz law? Lenz law tell that the induced EMF, the cause opposites every cause of producing it. So what does it mean? The cause of the EMF will be the opposite of the every cause of producing it. So what is the cause of the EMF production? Rate of change of flux. So if there is a rate of change of flux, the EMF direction will be such that it will oppose its cause. It will oppose its cause. So this is the known as the, you can see this is a north, this magnets is the south pole and north pole, and you can also see this, and you can see the coils are rotating. So as a result there will be the EMF, and what is the direction of the EMF? EMF direction will be such that it will oppose the change in the magnetic flux which causes the EMF. So if we write them, as I told that Maxwell's give the mathematical equation, so it came from the basic Gauss law. What does a Gauss law tells? The Gauss law for the first Gauss law tells about the electric coils. What is that? The number of electric lines of flux psi is equals to the charge enclosed. If a charge is enclosed in a closed path, number of lines of flux is equals to the charge enclosed. And charge enclosed can be written as the d dot ds. What is d dot ds? D is the flux density for the electric charge. Later it has been modified for the pure magnetic field. And what it came? That this is the magnetic flux. Magnetic flux is equal to B dot ds. So B dot ds don't need any closed path because magnetic flux can flow in the open path as well as the closed path. Then this is the first thing of the modified Gauss law. We will not tell the Gauss law, better to tell it is the modified Gauss law. So again from the Faraday's law, what we got? We got E is equal to minus d phi by dt. And what is phi? Phi is again we got integration of B dot ds. So we are substituting the phi according to the integration of B dot ds into dt. And why this minus? This minus sign is for the Lenz law. Now, if we know from the definition of the electric potential that electric EMF, actually as I told that the EMF is same as the voltage. Mathematically it is same as the voltage of an equation. And what is voltage? Voltage is nothing but the E dot dl. What is E? E is the field. If there is an electrical field, this is an electric field intensity. Better to write electric field intensity. So E, we got two equation, E dot dl, and previously we got E dot dl is equal to dB ds by dt. Now this side the integration is ds, means surface integral. This is the line integral. So if we want to make it in a one line, so we will write it in the Stokes theorem. And the Stokes theorem tells that the we can change it as the grad dot E dot dl is equal to grad cross E ds. This is the Stokes theorem. Already we have discussed in the previous lectures. So we can write that grad cross E ds is equal to dB ds by dt. So ds will cancel out both side, integration also cancel out both side, and we will get grad cross E is equal to del B by del T. And we can write it like that: grad cross E. E is the electric field intensity, d H by dt into mu, as B is equal to mu into H. We know B is equal to, so this is the relation between the electric field intensity with the magnetic field intensity. This is known as the Maxwell's fourth equation, or the vector form of the Faraday's law. As I told, Faraday did everything in the experimentally, but the mathematics behind, or the physics behind it, will be first discussed by the Maxwell. Next, we will go for a problem. What is the problem? A square loop wire of 50 centimeter into 50 centimeter is placed in an alternating field. So alternating field means the field due to the alternating current have the maximum intensity of 10 ampere per meter. So what type of intensity is this? This is the ampere per meter, means this is the H. H is equal to 10 ampere per meter. If the plane of the loop, I am writing, change the color. Now, if the plane of the loop is perpendicular to the magnetic field and varying at a frequency of the 10 megahertz. Okay, so plane is perpendicular means 90 degree, and it is the if a field is 90 degree means the maximum amount of flux cut is there. You can see, if this is a magnetic field and this is the north pole and south pole, the field is this is one north pole I am drawing here. This is a north pole and this is a south pole. So there are some electric lines of flux. You can see my right hand is showing the electric lines of force like this. Now, if any coil, like the plane is the coil, if the coil is in between this, the number of flux cutting is 0 because it is the parallel. But if the coil is like the perpendicular, what will happen? All the lines of flux starting from here to here will cut the total coil. So that's why we are taking here perpendicular to the magnetic field. The maximum amount of flux cutting is there. So first, what is the formula of the induced EMF? We know E is equal to minus d phi by dt. First, what is dt? We know dt means time. Here it is given the frequency. What is the frequency? Frequency is equal to 10 mega hertz. 10 into 10 to the power 6 hertz. What is the frequency? Frequency means 1 by time period. So already we got 1 by time period is the value is 10 into 10 to the power 6. Now we have to calculate the phi. How to calculate the phi? We know phi is equal to, what is phi? Phi is equal to B, flux density into cross-sectional area. What is the value of the cross-sectional area? 50 centimeter into 50 centimeter. So A is equal to 50 into 10 to the power minus 2 into 50 into 10 to the power minus 2 meter square. Remember one thing, we are using only the SI unit, so we will always take the unit in the meters, not in the centimeter. So 50 into 50 means 2500 into 10 to the power minus 4 meter square. Now we have to calculate the B. How to calculate the B? B we can calculate that we know, I am changing the color again so that it is easy. So how to calculate the B? We know B is equal to mu into H. Mu into H, and H value is given as 10 ampere per meter. What is the value of mu? Mu value is 4 pi into 10 to the power minus 7 into 10. So we got the value of B, we got the value of A, value of B, value of A, we will get the 5, we got 1 by T. So if we write 1 by 1, H is equal to 10 ampere per meter. What is B then? B is equal to mu into H is equal to 4 pi into 10 to the power minus 7 into 10. Then what is A? A is equal to 50 into 50 into 10 to the power minus 4. 2500 into 10 to the power minus 4 meter square, and we got 1 by T is equal to frequency is equal to 10 into 10 to the power 6 hertz. And what is phi? Phi is equal to B into A. 2500 into 4 pi into 10 to the power minus 7 into 10 to the power minus 4. So what is the EMF now? So what is the EMF now? EMF is equal to minus d phi by dt. D phi value is 1 by T we got, so it will be 10 into 10 to the power 6. So 10 to the power 10 pi into 10 to the power minus 11, 0.314 volt. So this is the calculation. Next is the types of EMF. EMF is basically two types. One is called the induced EMF. Another one is induced EMF is basically two types. One is statically induced EMF. Another one is the dynamically induced EMF. So induced EMF we can get from the Faraday's law. It is two types. What is the statically induced EMF? The conductors are stationary and flux is variable. The coil is fixed. We are changing the magnetic field. This is called the statically. The another name is called the transformer EMF. So in the case of the transformer, the coils are fixed and the flux means that we are giving the AC current in the transformer. Current is flowing in the conductor and it is inducing the EMF. So conductors are fixed. We are not moving the conductors. The current, the source current is the rotating. In the dynamically induced EMF, the conductors are rotating and the flux are constant. This is known as the generated EMF. So what is the meaning of the generated EMF? That as we told here, North Pole and South Poles are there. These are fixed. This is called the stator of a generator. This is stator came from the word static. So stator, and there are North Pole and South Pole. So we are using the prime mover, we are rotating the coils. But in the case of the transformer, the coils are fixed. We are giving the AC current and whatever the flux is generating, that is variable. Next is what is the dynamically induced EMF or motional induced EMF? In order to generate the induced EMF, dynamically induced EMF, the magnetic field system must be kept stationary while the coils or conductors are moving. If the aforementioned process are followed, the conductor cuts the magnetic fields, there is a rate of change of flux, and as a result some EMF will be induced. So what is the EMF? The EMF value is the BLV sin theta. The potential, the maximum value which is induced in this case is can be written as the EBLV sin theta. What is B? B is nothing but the, what is B? B is the maximum flux density. What is B? B is the velocity, not, this is the velocity, in how much speed it is rotating. And what is L? L is the length. What is theta? Theta is the angle between the conductor and field. How much flux it is cutting conductor and field. You can see, as I told, if the conductors in the parallel to the lines of flux, the cutting of the flux is 0, so sine 0. But it is 90 degree, the cutting of the flux is maximum, so it is sine theta is equal to 1. But what will happen if this coil is in this position? Because it is rotating continuously, it is changing its position, so this angle will be varying. This angle is the theta. And how we got this equation? Just one example. We know E is equal to d phi by dt. We are not taking the direction, we are taking the only the scalar quantity. What is then? D by dt is equal to B into A. B is the flux density, and what is A? A is the, what is A? A is the cross sectional area. Next we can write here E is equal to D B. What is A? A is equal to length into width by dt. So we can write B L, then dw by dt, the rotating of the width side. So this is the, actually this is nothing but the length by time, displacement by time. We can write B L V, and how much it is cutting, we can get it from the sine theta angle. So this is called the dynamically induced EMF. Example, as I told, motors and generators. So that only we are discussing here. This is a coil, X is the length, D is the, now we are doing it for an magnetic field. So this is the X and this is the D. So we can write the flux is equal to B into A. So V into D into X, not dx, D into X. D is the width, X is the length. What is F? F is equal to Q V cross B. We can also write Q is equal to V cross B. So F by Q is equal to V cross B, and force per charge, this is from the Coulomb's law. We can write E V cross B. So E is equal to, as this is a cross product, V B V B L sin theta, and what is the maximum value? B V L sin theta when theta is equal to 90 degree. Now you may ask how we are getting the L. L we are getting from the value of the B, as I told in the earlier. And how we are getting the sin theta? Because it is a cross product of V cross B. Now we are telling about the statically induced EMF. In order to generate a statically induced EMF, the magnetic field must be rotating and the conductors are in the static condition. If the conductor experience any force or any flux, we can tell this is a statically induced EMF. So what is the example? You can see here. So here this is the field which is rotating and the flux are constant. Consider a loop of area A in the region of space of uniform flux field B. We are not removing the, and it is rotating with an angular velocity of A. The conductor is fixed but the field is rotating. What is the example? The example is transformer. So what is the equation of the statically induced EMF? Statically induced EMF, we can write E is equal to integration of E dot dl. E dot dl is equal to minus n d phi by dt, and phi is equal to pi m sine omega t. We know that the flux, as this is a, as I told, the flux is the alternating flux, so it is in the AC. So phi is equal to phi m sine omega t, and E is equal to minus n d phi dt, and as E is equal to same as equal to potential, we can write E dot dl. So if we compare the both line, we can write minus n d phi m sin omega t n phi m omega cos omega t, and this is the main EMF equation of a transformer also. So we will do one small problems. A conductor of length 100 centimeter moves to a right angle to an uniform field of strength 10,000 lines per centimeter square. What is the meaning of 10,000 lines per centimeter square? It means that the flux lines is the 10,000. Okay, with a velocity of 50 meters per second. So what is the velocity? The velocity is the 50 meter per second. Calculate the and it is not 5 because it is given lines per centimeter square. So this is the not 5, we can write it B. B is equal to 10,000 Weber per meter square. And what is the length? Length is given as 100 centimeter, means 1 meter. As I told, all the units should be in the SI unit. Now compute also the value of the induced EMF if the conductor moves at the 30 degree. First calculate the EMF induced in it, and it is in the right angles. So we know E is equal to BLV sine theta. In the first case, theta is equal to 90 degree. So V L V sine 90. So it will come, whatever it is coming, 50,000. Sorry, it is given in the centimeter square. So we have to make it in the meter square. Sorry. So it will be 10 to the power minus 4. Meter square means 10 to the power minus 4. 10 to the power 4. So it will comes once 10 to the power minus 4. So 5 volt. If it is the theta is equal to 30 degree, the second case theta is equal to 30 degree, what will happen? In the case of the second case, B L V sine 30 degree. So what is the value? 50,000 into 10 to the power minus 4, and sine 30 is equal to half. So it will come 2.5 volt. Next, we will discuss about the current. So current, as I discussed in the discussion of in the time of unit 2, current is basically 3 types: conduction current, convention current, and displacement current. So first we will discuss about the conduction current. Conduction current means if we give any force, the electrons will start to move in the closed path. Like in our home, we are giving one switch. So this is the force we are giving. It will make a closed path and we are giving some voltage. What will happen? The electrons will start to flow and it will flow throughout the closed path. This is called the conduction current. What is the convention current? Convention current means if the electron flows naturally and there will be a current is there, then we will call the convention current. In the time of the cloudy day, when some clouds are there, it will induce some electrons. If the clouds are negatively charged, it will induce some positive charge on the earth. And as a result, due to this is a closed path, it will create some current will flow, which is called the lightning. And third one is the displacement current. Displacement current is happens in the case of an what is called this one? This is called the insulator, or we can tell this is in when in the case of a capacitor. What will happen in there? Generally, the flow of current is very less in the case of the dielectric. In the capacitor, in the case of the capacitor, between two conduction wires there is some dielectric medium, so there is a small amount of current is there. This current, that's leakage current, is known as the displacement current. The amount of the displacement current is very low, and the value of the conduction current, if there are two parallel paths, if we connect it within a voltage, so this path, the current will flow is called the conduction current. But if any little amount of current is flowing in between the dielectric medium, it is called the displacement current. This is the conduction current and this is the displacement current. So what is the value of the conduction current? Epsilon A by D, and it is called the, and JC is known as the conduction current density. Then what is the displacement current density? So what is the conduction current density? Conduction current density refers to the amount of current flowing on a surface of a conductor in a time t. If the total current is I is coming, we can think there is two parts. One is called IR. One is called IR. Another, this is the IR. Another part is the IC. And I, total current I has two parts. IR is the conduction current and IC is the displacement current. So what is the total current if we divide everything with the J? So I by A is equal to J. IR by A is known as the JR and IC by A is the JC. What is the meaning of JC? This is the displacement current. And this is the conduction current. So this is the last problem of the today's class. In a material which the sigma is equal to 5 ohm per meter, sigma is equal to 5 ohm meter, and sigma r is equal to 1. Electric field intensity is given as 250 sin 10 to the power 10 t. Find the conduction current and displacement current. First, we will discuss about the conduction current. What is the meaning of the conduction current? So, first we will discuss about the displacement current. So, displacement current we write by JC as it flows through the capacitor is equal to sigma into E, or we can know the sigma R value, the relative this one. So sigma into E, and what is the value of the sigma value we know, E value we know, we can get the value of the JC. And what is JD? JD is equal to, as we discussed here, what is JC? JC is equal to also del D by del T. We can calculate like this also. Jc is equal to delta D by delta T. Delta, what is D? D is nothing but the epsilon into E. Or here it is written as sigma epsilon into E. And what is Jd? Sigma into E. So from, if we calculate these two, we can get the current. So this is the, so the we have discussed in the, so in the today's class we have discussed about, so in the today's class we have discussed about the what is the Faraday, what is the field, time varying field, what is the Faraday's law, and what is the induced EMF, what is the displacement current, and what is the conduction current, vector, the Faraday's law in the vector form, or again we can tell it as the Maxwell's fourth equation. So up to this is today's class. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.